Okay. Okay, so in the last class we were looking at this differential amplifier where we had a current mirror, a PMOS current mirror added at the load side. And I label the transistors this way. So let me copy paste this and keep it. Okay, and we saw that although this circuit is asymmetrical, by contradiction, we saw that the only stable operating point here is when I1 is equal to I0, I2, right? And that was basically half the tail current you have here. And this meant that even the drain voltages here, which I'll call VD1 and VD2, they are also equal. And what was it equal to? Yeah, if I call this supply as VDD, it is basically the supply minus the source to gate drop of the PMOS transistor. So I'll write it like this: source to gate of the transistor M3 when it is biased at a current of I0 by 2. That's the notation we'll follow. Okay, great. And we also looked at the small signal again. And as I mentioned, here no point in looking at common mode and differential half circuits because no, so no point here in looking at symmetry because circuit itself is not symmetrical. So we thought we'll just go ahead with assuming two inputs V1 and V2, and I took a slightly different approach to find the gain. That is, I told that we have a block GM. Let me reverse the signs, and then it has an output impedance, and this is what this opamp implements. And to find the small signal gain here, all I need to find are the transconductance GM and the output impedance R naught. And the output impedance you guys know how to find. And for finding the transconductance GM, we told we'll short circuit the output so that if you apply an input, say Vi, the current from the transconductor GM-Vi completely flows here. So you can measure the current, and based on the input you can find what is the GM. So let me quickly go through that calculation because I saw a lot of blank faces towards the end of the class. So again, I'll start with finding the short circuit GM first. So as we saw, we'll short circuit the output. Again, this is an incremental short circuit. We are not directly going to connect it to ground, please remember. And yeah, this is V1, V2. And I'll draw the incremental circuit here itself directly. So the supply is a short, the current source is an open. Okay. So and the current I out here, this is what we are interested to find, and this will obviously have contribution from both V1 and V2. So if you try to find the contribution from V1, if you see, this is the circuit we have, and at the source of M1 we seem to have an impedance, and that's 1 over Gm of the transistor M2 because its drain is shorted. So here we have a resistance 1 over Gm2. So we call this node Vx, this is Vx, and yeah, we derived what this voltage was. What was this? It was half of V1. And similarly, by superposition, even the contribution from V2 will be V2 by 2, so it's basically again the average of these two. Again, mind you, it is average of V1 plus V2 by 2 only when you are actually shorting this drain to ground. Else this need not be the case. Okay, right? So which means now we know the source voltage here, so I can find the incremental current. If I call this current I1, what is I1? It is Gm times the gate to source voltage. Gm1 times V1 minuses, so this is just V1 minus V2 by 2. So this current obviously cannot flow down, it's an open circuit. So the only path it has is to flow up like this, and it is a short circuit. So I0 will have one contribution from I1, and the story doesn't end because the same current I1 flows to the transistor M3, and it's a current mirror, so this also gets mirrored here. So basically we have 2 times I1 at the output, and so the short circuit GM was GM1. Okay, fine. So again, I'm just doing the incremental analysis directly using transistors like this, but if you're not comfortable, draw the small signal equivalent using voltage control current source and stuff and work it out, and once you are comfortable you will be able to do it like this directly. Okay, so next let's so next we'll quickly find the output impedance R out, and for this we'll have to apply a test voltage here and find what current it draws. Again, I'll draw the incremental circuit here itself. This is ground, this is open. Now this current IT has 2 contributions, one that is flowing down and one that is flowing up. Fine. So IT is basically, I'll say I up plus I down. So first let's quickly find what is I down. So if you look at what is the circuit looking down, so we have this, we have the transistor M2, and here is where we have the voltage VT applied, and looking here, what is the impedance? It is again 1 over Gm of the transistor M1, and that is true because the drain of this, what is the impedance? Yeah, it's small, but what is it? It is 1 by Gm of the transistor M3. Okay, this we already saw. If we have a transistor whose gate and drain are connected, the impedance is 1 by Gm. So this is a small impedance, so which means looking into the source of M1, the impedance is approximately 1 by Gm1. So the total impedance, which I will call R down, what is it now? It is basically the cascode. Again, these things you should start to remember now. For cascode, it's basically whatever resistance you have at the bottom plus the R out of the transistor you have. This is M2, so it's R02, plus the intrinsic gain of the transistor you have, which is GM2 R02, times the impedance you have at the bottom, which is by GM1. And I mean, remember, M1, M2 are identical transistors. Same is the story with M3 and M4. So GM2 is GM1, so this simplifies to 2 R02 GM1, and this, for all practical purposes, it's 2 R02, right? So the looking down, the impedance is 2 R02. So what is I down? VT by this impedance looking down, so it's VT by 2 R02. Okay, so let me remove these guys now. So now this current I down obviously cannot flow into the source, so it will take this path. So the same current I down flows into M3, so obviously it will also get mirrored onto M4. So I up will have a contribution from the down current, which is VT by 2 R02. Okay, but you also have the R0 of the transistor M4 connected here, right? So that will draw a current, and what will be that current? It is VT by R04, right? Because its drain is at VT and the resistance is R04. This is the current. So what is the total current we have? It's the sum of these two. So what is that? Yeah, it's basically VT by R02 plus VT by R04. So the output resistance is these two guys in parallel. Okay, so this is what we kind of did hurriedly at the end of the last class. So now let's paste this guy. So for this guy, now we know the short circuit GM is what? GM of the transistor M1, and the output resistance is R02 parallel R04. So the gain is approximately GM1 times R02 parallel R0. Okay. And yeah, so one thing to notice, although the output resistance looks like this doesn't come because you have R04 looking up and R02 looking down. So that's a common mistake people tend to make, and that's obviously not the case, because we saw looking down the resistor is not R02, it was actually 2 times R02. Okay, but finally the expression comes out like this. So, and compared to the case where we didn't have this diode connection, this was the earlier diffamp we had. In this case, what was the differential gain? It was basically the same thing by a factor of 2. Okay, and that happened because here we had the signal currents flowing in both the branches, but you took out the output from only one branch, so which means half the current was wasted. But here, by making this connection, although the output is taken from this branch, the current flowing here is also added here along with the current flowing here. Okay, I mean that might be evident from the way you calculate the short circuit GM, right? So here you see the current I1, it's flowing here like this, but also a copy of it is getting added from here. So you are actually reusing the current flowing in the left branch and adding it to the output side. Okay, and that's why you have the gain to be this. Okay.
What if that I0 is not the current source but that current mirror or something?
So you actually want a current source. If you put a current mirror, of course nothing will hold good now. You're saying, you're saying like this. This is, this is still fine. Correct. Then you'll have, now I assumed an ideal current source. If you have a real current source, which means if you have a transistor, then of course this analysis is not exactly valid. You'll have some contribution due to the output resistance of this transistor. Okay, but if it's much larger, this is the approximate result here. And obviously you want this current source to be ideal, so you try to make it as ideal as possible. Okay, so this transistor is, this configuration is quite popular, and this is sometimes called the 5 transistor opamp or 5 transistor OTA, right? Because you have the 4 transistors and the current source is the 5th transistor, or sometimes it's called the 5-pack OTA. Okay. And this is basically a single stage opamp, because you just have one transconductor here, which is this guy, M1 M2, converting the input voltage to a current. That current flows through this output resistance to generate the output voltage. Okay, so this is basically single stage opamp. And these single stage op-amps are actually quite useful if you want to drive a capacitive load. Okay, but let's say you want to drive a resistive load. So say I put a resistor RL here at the output. So what happens to the output resistance now? Output resistance is the resistance looking from the output side. So what happens to it now? RL will come in parallel simply. Okay, so if RL is small, the output resistance is going to drop down a lot, which means even the gain of the op-amp is also going to take a hit. So single stage op-amps, you use it to mostly drive capacitive loads, and might not be a great choice to drive a resistive load. Okay. Cool. So now let's look at some more details of this guy now. And for that, first let's actually resistive loads. So,
what do you mean by single stage?
Okay, I just mean that it just means that you just have one transconductance GM, right? Here the transconductance is all coming from M1 M2, so that you just have one transconductor which pushes current into an output resistance to generate an output voltage. If you have, say, one more stage at the output, it's a two stage. Okay, so now let's say I have an ideal op amp. And make a connection like this. Say it's Vi, it's R1 and R2. So what is the output voltage here? Huh? This is the inverting amplifier. Hopefully might be familiar to you, right? Yeah, it's an ideal op amp. I say it's an ideal op amp, okay? I mean, this is not easy, it's not difficult to derive, right? Because you know this is at 0 volt. So which means what is this voltage? 0, because op amp is a negative feedback. What is the current? Vi by R1. So this current obviously will have to flow through the resistor R2, and that's what generates the output voltage. Great. So now let's say I try to realize the same inverting amplifier using our ODA. So this is Vi, R1, R2. Okay. Now ideally you expect this is at 0, this will also be at 0 volt. But remember these go to the gates of a MOSFET, right? So if I apply 0 volt, will the transistors be in saturation? Not really, right? So obviously we can't apply a 0 volt here. So I need to apply some non-zero DC voltage, which I'll call VCM. Okay. So which means what will be this node at? That will also be at VCM. Okay. And usually we'll also then add the VCM to the input side, because remember the current we want to flow through R1 is Vi by R1. Okay. So only if you raise this also by VCM, the current will be Vi by R1. Okay, so let me write it clearly. Okay. So yeah, so let's say now I don't have the input, I just apply the DC bias at VCM. What will be the DC voltage at the output?
Is it ideal?
Sorry?
Is it ideal?
It's a GM block. Yeah, assume it's ideal for now as infinite gain. Huh? Why?
The current is 0. So
Yeah. So the point is simple, right? The current flowing here is 0. So which means 0 current flows here. One end is VCM, other is also obviously at VCM. Fine. Now on top of it, now you'll apply a small signal VI, and that's what will generate you the required stuff. Okay. So now let's actually find out what is the range of this input DC bias we can apply, so that in our OTA the transistors remain in saturation. Okay. So now I am only interested in the DC voltage, so both of them are at some VCM. Okay. And I mean this is called the input common mode range, or ICMR. It's not Indian Council of Medical Research, but yeah, this ICMR. Okay. Okay, so first, okay, by the way, before we go into this calculation, so for an NMOS transistor, what is the condition for it to be in saturation? Yeah, I think everyone is saying this, so I'll write it. Is that fine? Great. So which means I can say the drain voltage is greater than VG minus VTH. Okay, because this is basically this, right? So this is for NMOS, and similarly for PMOS, this everything just reverses. Okay, so drain to source is source to drain. I mean, you can remember it in any way you want, but I usually try to. That's all, simple. no need to change anything. So which means here you will find Vd is less than Vg plus mod Vth. Yeah, you can remember it in any form, but finally it all boils down to this. Great. So now let us say I keep okay, let me replace this also with the real transistor, so that we have the 5 transistor configuration, and I'll call it M0. Okay, so now let us say I keep reducing this input common mode voltage. Which of the transistors will start to cry? Huh? I mean, which of the transistors will have issues in remaining in saturation? If I keep reducing the input common mode, the DC here, which of the transistors will have problem in remaining in saturation region? M0. Why? Who told M0? Why?
The current should be the same.
Correct. This is carrying a current I0.
So the VGS should be same.
Correct.
If you have the DC, then the drain of M0 should be same.
Exactly. Okay. So what he is saying is, we know that this is carrying a current I0. So both the transistors M1 and M2, what is the bias current? I0 by 2. For carrying this current of I0 by 2, the transistors must have a fixed VGS, which I'll call VGS1 at I0 by 2. Right? So if I keep reducing the gate voltage, what will happen to Vx? Yeah, source voltage is Vx, so that will also reduce. Okay, and that if that reduces, for M0 it's a problem. Okay, so let us say the gate of M0 is at some VGS0, so that it is carrying a current I0. What is the minimum drain voltage? You can find here, right? It is basically the gate voltage minus a threshold. So it is VGS0 minus threshold of the transistor 0. Fine. So yeah, this is the minimum source voltage for the transistor M1. So what is the minimum gate voltage? I mean, I'm saying the source is at this minimum voltage. No, I mean, this is VCM minus or plus? Sorry, not VCM, sorry. This is, sorry, what is it? VGS of transistor M1 at I0 by 2 plus Vx minimum. So Vx minimum, I'll expand it completely. That is basically VGS0 minus VTH0. Okay, and yeah, one quick terminology. So this guy VGS minus VTH is usually called the VD sat, because it is the minimum drain to source voltage required for the transistor to be in saturation. Okay, this is just a terminology, or sometimes it is also called the overdrive voltage, VOV. Okay. So I'll simplify this as basically VGS1 at a current of I0 by 2 plus the VD sat of the transistor M0. Okay, great. So this is about the lower limit. Now if I keep increasing VCM, what will start creating issues? Which of the transistors will have issue? If I increase VCM here, M1, right? So because you know the drain voltage must be greater than the gate voltage. So if you keep increasing the gate voltage, at some point M1 is going to go out of saturation. So what is the maximum gate voltage you can have? You can look from here and say, what is the maximum gate voltage? VG, what is the maximum value VG can take? VD plus VTH, right? So the drain voltage of the transistor M1 plus 1 threshold voltage. And what is this VD1 voltage? It is basically the supply minus a source to gate, right? So it's basically VDD minus source to gate of the transistor M3 at a current I0 by 2. Is that okay? I mean, if you keep increasing the gate voltage of the transistor M1 beyond some point, do you know that for a transistor to remain in saturation, the drain voltage must be greater than gate minus threshold, right? If you keep increasing this guy, this limit can get violated.
You can happen to M2 also.
Yeah, M1, M2 is same, right? You know that this is also VD2 is also at VD1. So I can take for anything. It is just convenient to look at M1, that's all. Okay, so hopefully that's clear. So similarly, just like we have a range of the DC voltages that can be applied at the input, same thing will exist at the output side also, right? Because output is again a drain voltage, so you can't have arbitrary voltages there. So what I'll do is, so you'll similarly have an output common mode range. So this is basically the minimum and maximum DC voltage the output can have. I'll leave it as an exercise for you guys to work out. Okay. But so if I keep reducing the output voltage, if the output DC keeps reducing, which of the transistors will have issue? M2. Okay. So this will be determined by M2. Similarly, if I keep increasing the DC at V out, which of the transistors will have issues? M4, the PMOS transistor. Okay, so this will be determined by M4 in saturation. So using these, I'll please take it as an exercise and work out what is the minimum and maximum ranges. Okay, so now that we know more details about this guy, so let's try to see its behavior in closed loop. And before that, let's take a case here. So let us say this is an ideal transconductor GM. It has infinite output resistance. Okay, I'm not connecting to ground. So I put it in feedback like this. Fine, and this is the input. This is the output. And as we saw, the single stage OTS are good at driving capacitive load. So first let's only consider an output capacitance CL. It's a different color maybe. Okay, so let's say at the input I apply a step of delta V. Okay, so it's delta V U of t. So if I sketch the input, it's going to look like this. Okay, so this is basically t equal to 0, and at t equal to 0 the input is stepped up to delta V. Okay, so, and remember, for now assume this is an ideal OT, so it has infinite output resistance for now. So can you tell me how the output might look like? Or first of all, let's say for t less than 0, assume capacitor is discharged. So this till this point I know what is the output. Now tell me, after I apply this step, what will happen to the capacitance voltage?
Can you decrease better?
Why? Why is time constant infinite? Okay, let's come to that again. It's not infinite.
Linear charging, sir. Constant current will be flowing through the capacitor linear charge.
What is the current flowing through the capacitor?
GM into
GM times? GM times delta V times U of t minus V out, right? V out of t. So it's not a constant current, right? It depends on the output voltage. First of all, can the output voltage change instantaneously?
no.
Why?
Capacitor doesn't have
When will a capacitor allow a sudden change in its voltage? It will not allow at all. This is the IV relation for a capacitor, right? If the voltage across capacitor change instantly, yeah, V is some U of t, right? So what is the current then? It is some delta of t, okay, something times delta of t. So only if you have an impulse current, the capacitor voltage can change instantly. So here, can there be an impulsive current? Why? Why not?
Not practically possible.
No, I am saying it's an ideal GM, right? Assume that this can provide any amount of current you want. Then can this provide an impulsive current? Why? Huh?
Because the delta size limits cannot generate an impulsive current at a time.
No, I'm saying, okay, can you elaborate on that? This is an ideal OTA. What I'm saying is, any amount of current I want, let's say it can deliver. Okay, so what is the current it can deliver? We have already written it, right? This is the expression. So here, if the current has to be an impulse, so definitely one of these voltages must be an impulse, and obviously it's not the case. This is a step, and we are assuming that this is also going to be a step. So in this case, it's not possible. Okay. Yeah, so at least everyone is clear that the voltage at t equal to 0 plus, it's going to be 0, right? So let me write at t equal to 0 plus, V out 0 plus is 0. So what is the current then? I out of 0 plus? From this, right? This is I out of t. Gm times delta V. Fine? Okay. So at 0 plus, this Gm times delta V, this current flows into the capacitor. So it will start to charge, right? And as the capacitor charges, the output voltage increases. So what will happen to the current I out? That will reduce. So the rate at which capacitor charges will also reduce, and eventually it will settle to what voltage? Delta V. Is that fine? Okay. So yeah, so this is basically, it's a first order exponential settling behavior, right? And to characterize this first order settling, I need basically the voltage at t equal to 0 plus. I know what is V out of infinity, that is delta V. What is the last thing I need to characterize this rising exponential? Time constant, right? And what is the time constant here? There is no R out. R out is infinity. I mean, okay, intrinsic R out is infinity. Okay. So how will you find time constant? It's basically the capacitance times the resistance it sees. That much is clear.
Yes, sir.
And to find the resistance, this is the configuration we have. Here you have the capacitor. I just need to find what is the resistance looking here. And for this calculation, we can short the input because time constant is a property of the system. Doesn't depend on where you apply the input or whatever. Okay. So I mean, we can apply a test voltage here. So I apply, say, V test. What will be this voltage? That will also be V test. What will be the current flowing in this direction? Minus Gm V test. So current flowing here is plus Gm V test. Okay, I mean, this current cannot flow here, right? I mean, so this is plus Gm Vt. So what is the impedance now? 1 by Gm. Okay, so the impedance, I'll say Ro, I'll say R out. I mean, this shouldn't be surprising, right? You guys know, if you have a transistor, I connect its gate to drain, what is the impedance looking here? 1 by Gm. This is basically the same thing, isn't it? This is the plus terminal, minus terminal, this is the output. Or I mean, we can take it the other way, sorry, yeah. This is minus and this is plus. This shouldn't be a surprise. So time constant is now what? Oh, not 1 by CL by GM. Okay, 1 by GM times CL. So what is V out of T? Can you tell me what the expression is now? It is a first order settling starting from 0 volt and reaching to delta V. T by tau, of course, into U of T you have. Fine, right? Because you put T equal to 0 here, the output is 0. At T equal to infinity, it's delta V.
So, what does it mean to say that it has intrinsic?
Okay, I just mean that you don't have an explicit resistor R out here, that's all I mean. I mean, you know, GM will have its own output resistance. In this case, I am starting with infinite R out, that's all. Okay. Great. So now let us say I am interested in the rate at which the output increases. Okay, that is, I am interested in the slope. So at what time instant do you think this slope is maximum? Look at this waveform. This is the waveform for V out. At T equal to 0, right? Because, I mean, it's clear, right? At T equal to 0 is when you have the maximum rate and then it sort of slows down. So what is this maximum slope? I mean, of course, you can differentiate this. Delta V by tau. So that's basically delta V. What is tau? I mean, here what do you get? Delta V into? I mean, GM by CL. Okay. Okay. So why does this guy make sense? I mean, my question is, can I directly find it out without having to find V out of T? Because it looks awful lot of work, right? Let's say I want to find the slope at T equal to 0. And look, I am finding V out of T, differentiating it and then putting T equal to 0. So just by the information you have here on the left side, can you tell me what the slope might be? So everyone is, okay that the maximum slope is at T equal to 0 plus. Okay. At T equal to 0 plus, what is the current? No, but we already have found it, right? What is it? GM times delta V. Okay. So T equal to 0 plus, it looks like you have a current GM times delta V pushing into a capacitor CL. This is the equivalent circuit. You have a T equal to 0 plus. So what will happen to the voltage now in this case? I have a constant current pumping into a capacitor CL. The capacitor voltage will ramp up, and what is the slope of the ramp? I mean, everyone is, if I have a current I flowing into a capacitor C, what is the voltage? Constant current I. Voltage of capacitor is this guy, right? I am saying I is constant. What is it? It's basically I by C times T. And here I is GM times delta V, and okay, and this is the slope we have, right? Okay, so this is the maximum rate at which the output can rise. Okay, so here I have assumed R out to be infinity. Okay, so again I will give you as an exercise to include R out. By R out I mean the GM has an intrinsic output resistor, say R0. Okay, with this you please redo this calculation. Okay, but do you think let's say now I have an R out also, R0 also. R0 is the intrinsic output resistance of the GM. I mean, for our 5-pack, for our OTA we had some output resistance, right? R0 to parallel R04, something like that. So yeah, you work it out, but let us say even if I include this R0, can you comment about this slope at T equal to 0 plus? Why? So at T equal to 0 plus, you will have an extra R0 here. Okay.
That's like a short.
So now this current has two paths to flow. It can either flow through R0 or CL. At t equal to 0 plus, capacitor acts like a short. All the current will obviously flow through CL. So slope is not going to change. Okay. So irrespective of whether you have this intrinsic output resistance or not, the maximum slope is still Gm delta V by CL. Okay. So now let's look at a transistor. Okay. So this is the OTA we have. So this is the output. So what is the positive and negative terminals here? I mean, basically by positive I mean if I increase the positive terminal, current is pushed out, right? What is the positive terminal here? I mean, basically, if you increase the gate voltage, what will happen to the drain voltage? If you have an increment in the gate voltage, will you have a positive increment in the drain or a negative increment in the drain? What is the gain of a common source amplifier? Minus Gm times R0, right? So it's a negative increment. Okay. So if I increase this guy, this will drop. So this is the gate for M4 that is dropping. What will happen to the output? No. Again, from gate to drain, you have an inversion. Right? So this will increase. Is that logic okay? So what is plus and minus now? M1 is plus, okay, because I'm increasing M1 gate voltage, output is also increasing, okay. So this is basically the plus, minus. And the configuration we had was, the negative side is connected to the output, right here, okay. So basically you will have a feedback like this. And at the output you have obviously a capacitor CL. Okay. So now let's find out the maximum slope here again, right? And you know that the maximum slope, if I were to find the maximum slope, what time instant I should be looking at? 0 plus. So at t equal to 0 plus, you see that Vout is 0. So which means basically the feedback has not started to work. Okay. The capacitor was uncharged. At t equal to 0 plus also it is uncharged. So it's as if this guy is not doing anything still. So I can say that there is no feedback at t equal to 0 plus. Okay. Is that fine? So at t equal to 0 plus, there is no negative feedback, or no feedback has not started to kick in. Okay. So at t equal to 0 plus, I can say that this connection is not there for now, right? And V out of 0 plus is what? 0. And at the input we have stepped it up to delta V. Remember, okay? So V out was 0. This is also at 0 ideally, but of course you will have a bias here. So this is some VCM, right? And this is VCM plus delta V. Fine. Great. So now you know that the current flowing here is Gm delta V at t equal to 0 plus, that we saw now. So if I keep increasing delta V, looks like the current that is pushed into the capacitor at t equal to 0 plus will also increase, right? So let's say I increase delta V here. Which of these transistors, M1 or M2, will carry the higher current? The gate voltage of M1 is higher, so which means which will carry higher current? M1 will carry higher current, right? So let's say now M1 current will be higher, M2 will be smaller. If I keep increasing delta V more and more, what will happen? Sorry? Yes, what do you say?
M2 current will decrease.
M2 current will decrease. Let's say keep increasing delta V more and more, what will happen finally?
M2 will off.
No current will flow through M2, all the current will flow through, yeah, from M1 it will flow through CL. Okay, so I'll just say at delta V equal to some delta V max, all of I naught steer to M1. Okay, so which means current flowing through M2 is 0. So what region is M2 operating in then? It's in cutoff basically. Okay, so at this point, let's say delta V equal to delta V max. No, M2 is basically cut off. I can basically remove it out of the picture. Okay, all of the current is now flowing through M1 now, and that current is what is mirrored here, and it will flow through the capacitor. Okay, so what is the maximum current with which this OTA can charge our capacitor? I naught. So what is the maximum dV out by dt? I naught by CL. Okay, fine. So this maximum slope has jargon, it's called slew rate. It just says what is the maximum rate at which my opamp or the OTA can charge a capacitor and increase the output. Okay, and this is the positive slew rate because it says how the capacitor voltage increases, right? And in this case it's I naught by CL. Okay, so what happens is, now let's say you have, this is the time, this is V out. For very small delta V, the output will rise exponentially nicely like this and settle to delta V. Okay, now if I have a very very large delta V, ideally it is supposed to do this and settle to delta V, but our OTA has a limited current I naught, so which means it can charge only at a fixed rate, right? So for it will, for some time it will keep charging with a constant slope of I naught by CL, because that is the maximum current it can provide. Okay, but once this capacitor charges, I mean after t equal to 0 plus, the feedback is active. Fine. So once the capacitor starts to charge, the gate voltage of M2 will start to increase, and then slowly it will start to become active. Okay, so what will happen is, for some time the current flowing through the capacitor is I naught. It will charge linearly like this, and say at this point the voltage has risen high enough that the other transistor is also now active. Then it will follow the exponential settling like this and do this. Okay, is that fine? So basically, if the transistor can supply infinite current, it would have for any delta V, it will follow this. It will nicely follow the exponential behavior. That's basically what we derived for the ideal GM case. Here, right, this guy. But we see that if you have a very large delta V, it is easily possible that one of the transistors will become cut off. So the entire current here will get steered into the capacitor. So irrespective, I mean, you keep increasing delta V, doesn't matter, the maximum current it can provide is still I naught. So it will only keep pushing that current into the capacitor, and the output will increase linearly like this. Okay, and so as here I can see, as the output increases beyond some point, the gate voltage of the other transistor will also increase, and now that will start to contribute, and then we'll follow the exponential system.
Sir, we can also find out the maximum value of delta V at t equals to 0 plus.
Yeah, we'll do that now.
I naught by CL. I naught by CL.
No, we'll come to that. It's not exactly that actually. We'll find out. So this rate at which, this maximum rate at which the output can increase for a given capacitive load is called slew rate. Okay. So just like we have the positive slew rate, you can also have a negative slew rate, right? So what that is Yeah. So here we assume that this is the deal. Here we have VCM plus delta V. This was at VCM, and then you had the capacitor here, right? So now if let us say delta V is a negative step, so beyond some point what will happen? Basically if I keep increasing delta V, at some value of delta V, what will happen? M1 will be cut off. Okay, so this guy will now be out of the picture. So all of the current will flow like this. So what I am saying is, see, maybe I can draw it. So when you have a negative step like this, basically it will be at VCM to VCM minus delta V. Okay, the output will also start from this guy and then try to do this. But if you keep increasing this delta V more and more, then the gate voltage of this will be very, very small, the transistor M1, that it will become cut off. Then here remember, it is a discharging kind of behavior, right? So the rate at which the capacitor discharge is now constant again. We can only discharge at a fixed rate of what rate? I naught by CL with a negative slope, that's all. So this is the negative slew rate. So in this case it looks like both the positive and negative slew rates are equal, but this need not be the case all the time. Okay. In this configuration it turns out like that. Okay, great. So 10 more minutes, let me cover the last point. So again, the case we have is at one point we had VCM plus delta V, other is VCM, okay, and we saw that at some delta V equal to delta V max, so M2 is cut off and current in the transistor M1 is I naught. Okay, so let's quickly find out what is this delta V max. Okay, so when the input is equal to this maximum voltage, the transistor M2 is just entering cutoff. So if it is in cutoff, what can you say about the VGS of the transistor M2? Huh? VTH. I mean, it is just entering cutoff. VTH. Okay. So if the gate voltage of M2 is at VCM, what will be the source voltage Vx? I mean, we see VCM minus VTH. Is that okay? But notice that this is also equal to the source voltage of M1. So what is the current flowing in M1 now? I naught. When M2 is just cut off, I naught is flowing through M1. So Vx is also the gate voltage of M1 minus the VGS of M1 at a current of I naught. Is that fine? And this delta V is basically a delta V max, right? Because at this voltage, this happens. So from these two, can you tell me what is delta V max? Huh? I mean, this is also equal to Vx, right? We equate both of them and then VGS1 at I naught VTH. Okay. So if a transistor carries a current I naught, what is its gate to source voltage? I mean, in terms of the sizes and transistor properties. Square root of 2 times the current by UNC OXW by L plus VTH. Okay, so this minus VTH, these two cancel. This is what we have. And by the way, nominally, if things are all fine, what will be the operating point current flowing in M1? I naught by 2, right? So what is the gate to source voltage of M1? at a current of I naught by 2. I mean same thing, right? Square root of 2 times I naught by 2, so that's just I naught by same thing, mu n cox w by L plus Vth. Okay, so basically this guy I'll write it as square root 2 times fine. So from these two, can you tell me what is delta V max now? Oops. So I mean delta V max is square root 2 times this expression, and this expression from this, what is it? It's root 2 of the VGS minus VTH at a current of I naught by 2. Okay. So this, in other words, is the VD sat of the transistor M1 when it is carrying a current of I naught by 2. Okay. So the voltage is not I naught by Gm, because there you have assumed complete linear operation. Okay. The actual expression is this. So at this voltage, root 2 times the VGS minus VTH at a current of I naught by 2. If you apply that much of a step, then this complete current steering happens. Okay. So one last point. So now let us say I have applied that delta V max here. Okay. This is VCM plus this. This is VCM. Now we know all the current is flowing through M1. So I'll basically, for simplicity, I'll remove this guy. Okay. Say I call this voltage Vx. Now if I keep increasing this delta V beyond this point, what will happen to Vx? Huh? Yeah, I mean now it looks like what kind of a configuration it is now. I am applying delta V at the gate, considering the output from the source. Not common gate. I mean it's a source follower, right? I mean, see now the transistor carries a current of I naught, so it needs to maintain a fixed gate to source voltage. So we increase delta V, Vx will also increase. Okay. So if I plot the characteristics delta V versus Vx, the moment you exceed this delta V max, you just have a circuit like this. It's a simple source follower. So if you keep increasing delta V beyond this, Vx will also increase. And similarly, the negative side also you can argue the same way. For minus delta V max, you will have. Okay. And in between, you will have something like this. So what kind of a function do you think this is? I mean, do you know any mathematical function that closely resembles this? Huh? Okay, I mean, it's not this curve, right? I mean, that's what I was trying to correct. This is basically a linear line. Okay. This is simply like y equal to x. This is y equal to minus x. So what kind of a function do you think?
Hyperbola.
No, hyperbola is a curve, right?
No, it's like tangent. It goes to like. It will have.
Okay, probably I'll make it more clear. See, this is two straight lines and this guy. Huh? No, approximately something. I mean, see. Mod x. Fine. I mean, it's a straight line, right? At positive side, it's plus x. Negative side, it's minus x. Okay. So this basically implements a mod x function, right? So you'll have something like this. And if let's say if I apply a sinusoid, what will be the modulus of the sinusoid? I mean, it's 0. We'll have this, right? What is it? Yeah, it is. You can think of it like a rectifier, actually. Okay. So yeah. So if the sinusoid has a frequency, say f1, so what is the frequency of this guy? 2 times f1. That's fine. So this is a linear operation or a non-linear operation? Non-linear. What kind of non-linearity is it? I mean, I say y equal to x will give you just sine of that frequency. What should be the operation I do roughly so that I get a frequency 2 times f1? Huh?
This peak to peak must be inside the delta V.
Yeah. Assume that, yeah. I'm just saying for this guy, okay. It's a square, okay. So it will basically, you can have x square, x power 4, whatever you want, okay. So it has only even order terms, okay. So basically, if you take this diff amp and notice, if you apply a sinusoid and then you try to find what is Vx, you might have even order nonlinearities. Again, if like you mentioned, it has to exceed this delta V max range. Okay. And of course, you can also use it like a rectifier if you want, but that is not our main thing. It is like doing some side quest in a game, right? Our main focus is to make an opamp, but if you wish, you can take this and call the rectifier. Okay, so what I meant is, this part is fine, right? If I apply a sinusoid at a frequency f1, rectified output has 2 times f1. So to get a frequency 2 times f1 from an input frequency f1, the operation you will have to do, one simple operation is x square, right? That's what I meant. Okay, so we can stop here. Hopefully, yeah.